This video will discuss the limit of a function. Let's first start with the definition. This is the definition that we see from our textbook. We have our notation. The LIM represents the limit, and x will approach some value a, and that a is going to be a number. For our function, they could either list it by name, like f of x here, or they could actually write the algebraic statement of the function, like x minus 2, for example. And it's going to equal some value L, and that limit value will be a number if our limit does exist. Later on, we're going to discuss about when a limit may not exist, and in that case, we would say that the limit does not exist at that value. And essentially, what we're trying to say here is we're going to find the values of our function as they tend to get closer and closer to our value L. That L will be our y-coordinate. When x is getting closer and closer to the value of a from either side, but x does not equal a. And I know that seems a little bit tough. Why would we not let x equal a if we're trying to find the trend of behavior as x approaches a? And so the next example, I think, will help clarify that some. So here we have a rational function, x minus 1 over x squared minus 1. And this particular function has a hole in it. If we were to factor our denominator, we would see that there's a factor of x minus 1 that could cancel out, leaving a simplified form of 1 over x plus 1. So in a case like this, that would create a hole. So here we're seeing when x is 1, there's actually a hole in our graph. So there actually isn't any y value there. So this is where our limit would be helpful to approximate or calculate that y value. So what we can see, and the whole point of a limit is we're looking at the values of x when they get close to the value of our limit, both from the left and from the right. So we can see that if I look at the values of my function tending towards that x value of 1 from the left, which we can see in the table here, right? We started with 0.5, then 0.9, 0.99, 999, 999. We can see that the values of y are getting closer and closer to what looks like 0.5. And if I do the same process and get very close to my value of x being 1 from the right-hand side, so starting at 1.5 and then 1.1 and getting closer and closer to that value of 1, we can see our y value also tends towards that value of 0.5. And graphically, if we looked at our graph, we would see that the y-coordinate, if it did exist, would be at that value of 0.5. So that's the idea of a limit, is we're looking at the behavior of our graph and determining what would be the y value at that particular x that we're using for the limit. And it doesn't mean that your y value has to exist. Like in this instance, there actually isn't a point there. So the y couldn't actually equal 0.5, but the limit is estimating the behavior. So we know the behavior would tend towards that value of 0.5 for y. Now that's a very mathematical way of seeing the limit. I always like to put mathematical ideas into the context of something in real life. So an example that I thought of is my favorite yogurt shop. So there was a yogurt shop called Zynga in Colorado that used to run a promotion where if your frozen yogurt weighed 13.5 ounces, you would get it for free. And normally the yogurt costs 35 cents per ounce. So if we were to graph the cost of our yogurt, as the weight and ounces would go up, we would anticipate the cost to go up by that 35 cents per ounce. We would have this nice linear equation. However, because of that promotion, there's actually a jump in our graph. You wouldn't pay the normal cost for that 13.5 ounce yogurt. It would actually be for free. So your cost would be 0 in that case. So the idea of the limit here would be, what if the cost for the 13.5 ounce promotion ended? Right? What would be the cost that a customer would pay in that case? So I'm trying to estimate the y value for that hole that we see here. So I could estimate it. I could look at my approximate y value and know it's some cost just under $5, or I could calculate it based off of the situation. I know it's 35 cents per ounce, and I can multiply by the 13.5 ounces, and that would allow me to calculate the amount. So here, when I type it into my calculator, I can see the cost would be about $4.73. So that's the idea of a limit, is even if our value of that point doesn't exist, what is the behavior tending towards? So in this case, if they drop the promotion, my yogurt that would have been free for the 13.5 ounces would now cost me $4.73. So let's talk about when does the limit exist. So there's going to be some cases when a limit doesn't exist, and we'll see that later on in the course. But let's first look at the key criteria that we need to meet to make sure that our limit does exist. So we would say the limit does equal that value L, if and only if the limit to the left and to the right are that same value of L. So notationally, there is a notation for the left and the right. So if you see that little minus superscript on the A, that's the notation to say the limit from the left. And then the little superscript of a plus represents the limit to the right. So essentially what it's saying is the behavior has to tend towards the same y value for the overall limit to exist. I don't want to have it where my limit value from the left and from the right are different, because then I'm seeing two different trends in behavior. So to better illustrate that, let's look at this lovely piecewise function that we have here, and we'll calculate some left-hand and right-hand limits. So let's first start with our value here for the left-hand limit at 2. So I know it's a left-hand limit because I see that negative there. So I'm looking at the values just to the left of when x equals 2, and I'm going to estimate the y value there. So I can see that the y value would be 3. So we give our answer as being 3 for that limit. But from the right-hand side, which I know from the little plus sign on my superscript, I would look at the values just to the right of 2 and estimate the y value. This time it's 1. So what that means then is the limit at 2 is not going to exist, because if I notice here the limit from the left is 3, from the right is 1, they're not tending towards the same y value. And we can see that very clearly on our graph because we have this kind of jump in our function. My y value is 3 from the left-hand value of 2, but then it jumps down to a value of 1 on the right-hand side. So we would say that the limit does not exist. And the common way to abbreviate that is D and E. So don't be surprised in your textbook if you see that abbreviation. Now let's look at a slightly different case. Let's look at the value of the limit at 5. So here on the left-hand side of 5, I'm seeing that my y value would be 2. Then from the right-hand side, I'm getting the same y value of 2. Now this time my left and right-hand limits are matching. I'm getting a value of 2 for both. So that is an instance where the limit does exist, and the limit value would be that same y value that we're getting, in this case 2. Now if you look at your graph, you may be a little curious about that, because we do have a point or a y value at 5. So if I had asked this question differently, if I had said what is the function value at 5, well there I would give a different answer. I'd be giving the y coordinate of that point that we see there, which is 1. So that's a key difference here, is the limit is talking about the trend of behavior for the y. They're not actually asking for the output. So if you had a jump here like what we see, I have a hole there, and then a filled in dot underneath. In that instance, I don't really care about that extra dot. I don't care about the y value of 1 that function is taking on. I'm caring about the trend of behavior, and the trend of behavior is that approaching from the left and the right of that value of 5, I'm seeing a y coordinate of 2. So that can sometimes confuse people to see that the y coordinate is different from the limit, but that's totally fine. The limit is talking about behavior and what our y's are approaching, and that may be different from the actual function value there at 1. So let me finish off this video about talking when a limit does not exist. So we saw the first criteria, if the left and right hand limits do not match, like what we saw here on our graph at 2, that's when we say a limit does not exist. The second criteria is if my limit is approaching without bound. So here if I wanted to calculate the limit as x approaches 0 of my function, I would say that it does not exist because I'm seeing this asymptotic behavior. It's increasing without bound on the left and right hand side. And then the third option is kind of the most interesting one. Here if I calculate the limit at 0, I wouldn't be able to do it because I have a highly oscillating function. It's changing far too rapidly for me to know actually what's happening within the function.